Today's mindless blabbering is going to be all about carbonyl additions. We've already seen an example of a carbonyl addition as it would occur to an aldehyde or ketone in the case of a Grignard, right? In the case of something that has basic conditions. Today will be our first example of the slightly more laborious process of showing a mechanism in acidic conditions. In addition to that, we are going to learn a little bit about a new concept in synthesis called a protecting group. Okay, so I just picked out a random ketone here, and what we've done is we've produced what's known as a Ketal group. Turns out this Ketal group is a pretty important protecting group in synthesis, because if you judiciously use this kind of strategy, what you can do is you can kind of hide this carbonyl from, let's say, some other Grignard addition, right? Let's say that there's something else that you want the Grignard to act on. This is a way to, in a pretty simple fashion, kind of disguise this thing so that the reaction or the Grignard won't recognize it as a true ketone. And then the second that you've done your Grignard reaction, you can then clip this thing off, right? And it turns out that this is an example of a reversible reaction where the second that this thing gets any kind of a source of H2O with catalytic acid here, this group is going to come off, right? That's called a true hydrolysis. So the steps that I'm going to show you are for going this direction, but you should be able to do the same exact set of mechanistic steps, or similar set of mechanistic steps for the hydrolysis reaction. One other thing I should probably mention is that I just like this as kind of a good synthetic protecting group. Technically, we could have done it if we just had these things both as like, just plain old alcohols as opposed to a diol. The only difference is that your protecting group would not be linked together right here. So in other words, if this thing, let's say, was two equivalents of methanol, you'd end up with this ketal having an OCH3 and an OCH3. That's just something that, it just doesn't seem like useful to kind of go through that in any kind of detail, but I should mention it. So, one of the things you'll remember, in basic conditions, we had a strong enough nucleophile to just punch that carbon, right? So what we need to do, and the reason that H plus needs to be there, is that we need to sweeten the pot a little bit, right? It turns out in biochemistry and a whole bunch of different fields, that very first step, that acidification of a media, does make those compounds a lot more reactive. And the reason is because when we reach out with our electrons, we end up with drastically increasing the electrophilicity of that particular carbon. So as before, this as a nucleophile wasn't strong enough, and suddenly now that we've protonated this thing, it's more than activated towards an attack by that set of electrons. All right, so I wrote out the next few steps of this mechanism just to make our lives a little bit easier here. So what you'll notice here is that I had to invoke a second equivalent of this reagent, and really all I'm using it for is a way to move this H over to the hemi part of this thing. You'll see in a lot of texts that they'll just simply go from this lone electron pair to that hydrogen, right, and do it kind of an intramolecular step. That's not technically correct, and it also kind of blows past a pretty important thing in carbohydrate chemistry, which is called the hemiacetal. Obviously, a hemiacetal is halfway to a ketal, right? So we haven't completely attached everything yet. There's still an OH bonded. And it turns out the hemiketal, as I said, is a pretty important intermediate in a biochemical context, so I'm going to go ahead and leave it there. Another thing which I wanted to mention is that if this thing was an H, right, in other words, this was an aldehyde, this is called an acetal as opposed to a ketal, right? So aldehydes produce acetals where ketones produce ketals, and obviously then this would be a hemiacetal. Just kind of a minor thing to talk about there. Quite honestly, a lot of people kind of overuse acetal when they're actually talking about ketals, but I'm the only one that probably cares about that. So now that we've moved that hydrogen over to that side, we can finish this mechanism and hopefully follow the bouncing ball here. And just like we saw before, the fact that this oxygen has a positive charge makes that carbon that much more electrophilic. So we are going to reach over and close the ring And then in order to get to our final product here, we're going to invoke another equivalent of our reagent and show it ripping off that hydrogen. Okay, and once again, this very last step isn't always drawn in all of that detail. Like then, for instance, they'll just kind of show the hydrogen falling off. But I like to have kind of that two-handed clap idea for these kinds of things. So keep in mind what I said in the beginning, right? We showed the formation of a ketal, but it turns out this is actually a reversible reaction, so that if we had acidified water, we could actually rip this group off, right? That's kind of the off switch for this particular protecting group, which is common to all protecting groups. They all kind of have their own little off switch. So you should be able to follow this reaction through the exact opposite direction. One thing that's really important, which we're going to be picking up on as a theme all throughout the next couple of terms here, if we have something in basic conditions, all of the intermediates that I show are going to be either negatively charged or neutrally charged. And there is kind of an exception with a cool little thing known as nitrogen, but we're not going to worry about that just yet. And then in an acidic condition, one good way to know whether or not you're doing the mechanisms correctly is if all of your intermediates are either positive or neutrally charged, right? And so in acidic, positive or neutrally charged, also much longer mechanisms in general, right? This is a lot longer than that Grignard reaction we saw. And then in basic, either negative or neutrally charged intermediates. So hopefully this will help your mechanisms